Hello class, welcome to the Stat 211 lecture, the first lecture of this course. Today we have a couple of topics we'd like to cover. First, we want to talk about what is statistics. Second, the importance of logical data structuring. Third, types of variables, and then an intro into data visualizations. Let's get started. So the best way to start an introduction to statistics course is to talk about what is statistics. So there's going to be two terms called statistics that we'll use in this class. The first one is the subject, statistics. So statistics is the science of collecting, organizing, and interpreting data. That word data, though small, does kind of have a powerful meaning in this course. So data is a collection of observed values representing one or more characteristics of some objects or units. Basically, we collect data to understand our world. In this course, we are mostly focused on the interpreting data part of statistics, as opposed to the collecting and organizing part. In general, we will spend the first few weeks looking at different ways of organizing data, and then we will review best practices for collecting meaningful data before focusing on the interpreting part. As stated in the previous slide, statistics is the science of collecting, organizing, and interpreting data. Like most sciences, there are several subgroups and subdisciplines that are involved in the science of statistics. We will touch on several of these different subgroups in this course. I often feel that the difficulty in Stat 211 doesn't come with any individual topic, so rather the quantity of the material. Because there is a lot of material in this class, but again, I don't think that like any individual topic is particularly challenging, it's just the amount of it. And really, the goal of this course is to introduce everyone to the basics of statistics. And so we are going to give you a little bit of a spoonful of all the different subgroups so that you have an understanding moving forward in your careers. As I mentioned before, we're going to hear the term statistics in two different ways. One as the subject matter, statistics, but there is also these things that we call statistics. In our world, we often take samples from a larger population. The values we calculate from our sample is called a statistic. A value calculated from a population is called a parameter. So what you can think about is if I were to poll everybody in this class about the quality of the food in the layer, that value would be a statistic. If I were to poll everyone at WVU about the quality of the food in the layer, that would be a parameter because I've polled everybody in the population. So in statistics, there is kind of a specific pattern of study. So as always, we start in the beginning and we begin by identifying our goals. What is our purpose? What are we trying to understand? From our goals, we have to identify and look at our entire population. Now, unfortunately, it is not often possible for us to poll everyone in a population. Populations are usually too large to do that practically, and polling everybody in a population is generally very expensive and time-consuming. There is a reason that we, as statisticians, only take a census every 10 years. Fun fact, and good vocabulary term, when you are able to poll or measure every item, thing, or person in a population, that is called a census. And again, censuses are usually not possible. So instead, we have to, step 2, draw from a population and collect a sample. Ideally, this sample is representative of the full population, just smaller. From that sample, we can move to step 3, where we collect our raw data and are able to summarize our sample, aka calculate sample statistics. Using these sample statistics, we can then make inferences about our population and estimate our population parameters. From there, we can draw conclusions about the entire population. If you're not fully clear on this, take a few seconds to look at it, and if not, definitely we'll keep talking about this. Because the fact of the matter is that the relationship between samples and populations are key to our understanding of statistics, and they really go back and forth for us. We use samples and statistics to make inferences about populations and parameters. We have an easier time collecting a sample and calculating a sample statistic and being able to use that to understand a population and the population parameters. When we're in the opposite situation, where we know the population and the population parameters, but we want to have an understanding of a sample we might pull, we call that probability. The term probability is something you're probably quite familiar with. So to kind of have an understanding of this visually, so in our first circle we have population, and underneath it we have a few population parameters. In statistics, there are certain Greek letters and normal alphabetic letters that we use to represent and denote different statistics and parameters. In statistics, mu, the Greek letter mu, stands for the population mean. Sigma, the Greek letter sigma, which kind of looks like an O with a little hat, is the population standard deviation. And then kind of a cursive P is the population proportion. Again, when we have a population and we're going to a sample, we call that probability. When we take a look at our sample, if we have a normal letter with a bar over it, that stands for the sample mean. You'll most often see this attached to either an X or a Y. For a sample standard deviation, we use the small letter S. For a sample proportion, we use a P, and we have a caret, or what kind of looks like a little hat, triangle hat on top of it. We do pronounce this actually as hat, so P hat stands for the sample proportion. You might want to have these 6 symbols and their corresponding meaning written down somewhere, because you will see them throughout this course. As I just mentioned, when we have a population and we're going to a sample, we call that probability. When we're taking a sample to try to understand the population, that is called inference. This brings us to our second objective of today, which is the importance of logical data structuring. Here are the basics. In statistics, we like to collect information on subjects. That information we often known as a variable, which is a characteristic that differs from one subject to the next. Some of these could be age, grade level, number of hours you study, or a score on a final exam. The values of the variables that we obtain are the data. An individual value is called an observation. All the information is collected to form a data set. It is very important for us to organize our data and our data set in a logical manner. taking a look at this data set, what do you see? Personally, I find this data set pretty hard to understand. I see state, country, names, random numbers, not even like consistently random numbers. Some of these look like possibly money, maybe ID things, not sure. And then we have these randoms, N's and Y's, which might mean no's and yeses. But either way, like looking at this, I'd have a very hard time determining what we're even looking at. But organized in a way that's understandable, we can see exactly what we're looking at. We have order numbers, names of the purchasers, state and country of purchase, the price, area code, where the item was downloaded, gift, ASIN, and artist. So even though I don't have a title, I'm looking at this and I'm saying, oh, they must have been downloading music. In fact, given the prices, I'm going to estimate that this data set is an old school list of downloading iTunes, because there was a time when you could download songs on iTunes for 99 cents. So I'm going with that. Again, and that's probably right. Again, if we had a title, that would be more clear, but either way, even without a title, we're still able to gather tons of information just on having a clear and informative data structure, particularly having very helpful data headings. So as I mentioned, we are collecting information on variables, which means we now need to know what kind of variables we'll be looking at. So we can recall that characteristics recorded about each individual are called variables. To understand the collection of these variables, we need to go take a step back and understand what kind of studies we might be looking at and what kind of variables they might produce. So in general, there are two types of studies we think about in statistics. One is observational studies, the second, experimental studies. Observational studies are ones where researchers observe the effect of a risk factor, diagnostic test, treatment, or other intervention without trying to change who is or who isn't exposed to it. Experimental studies are ones where researchers impose treatments and controls on the process and then observe the results and take measurements. So observational studies happen a lot of times in, oh my goodness, my brain just blanked. You can see them happening in medicine, particularly when we have events that have a rare outcome. So a pediatrician might do an observational study on seeing children that are born with, say, Down syndrome. Where experimental studies you can think of as something you might see with a farmer trying to determine what pesticide, fertilizer, and seed type produces the greatest yield. With these studies comes two general types of variables, qualitative and quantitative. Qualitative variables are ones that yield non-numerical information. These are also known as categorical variables. To be honest, I prefer using the term categorical variables to qualitative because I feel like the term qualitative and quantitative are similar enough sounding that people can get easily confused. So generally speaking, you'll hear me use the term categorical. Type of categorical information you might see is gender or biological sex, race, seed type, fertilizer type. Quantitative variables, on the other hand, are variables that yield numerical measurements. The quantitate variables can be further classified as discrete or continuous. Discrete variables are countable, continuous variables are going on continuously. So to have a better understanding of the discrete variables, as I said, these are values that are countable. They contain a finite number of values. These discrete variables typically record the amount or degree of something, such as the number of coins in your wallet or the number of animals in the zoo. You can easily count these. There is no half. These are just, there are 10 coins in your wallet. No ifs, ands, or buts kind of thing. Continuous variables are numeric variables that have an infinite number of values between any two values. And it typically records something that has an infinite number of possibilities. So, for example, the length of time waiting for a bus is considered a continuous variable. Because if you arrive at a bus stop, you could be waiting 2 minutes, 5 minutes, 30 seconds, 5.23567 minutes. The bus could never come. You could be waiting an infinite amount of time. We also have something called ordinal variables. An ordinal variable is one that reports order without natural units. One of the most commonly used one is the 5-point Likert scale, which is that strongly disagree, disagree, neutral, agree, strongly agree that you usually see in surveys. Another one you might be familiar with is Olympic rank, gold, silver, bronze. I do want to be careful, just so you're aware, that sometimes we do attach numbers to ordinal variables. If we think that 5-point Likert scale, sometimes instead of going strongly disagree, disagree, all the way to strongly agree, we give it numbers, rank things on a scale from 1 to 5. 5 being strongly agree, 1 being strongly disagree. There's another type of variables that can sometimes get people confused as to whether it is a categorical variable or a quantitative variable, and that is an identifier variable. These are a variable where each individual receives a unique value. Identifier variables are part of metadata or data about the data. Sometimes identifier variables like a student ID is purely numeric, but it is unique to each individual and is their identifier, and is something that we actually treat as categorical even though it has numbers. Your zip code or area code in a cell phone, again, these are numbers, but those numbers are actually identifiers. They represent a particular area where you live. As I said, as we go through this course, we're going to have a goal of trying to understand, explain, and interpret the data. Our first introduction to understanding the data is the 6 W's of data description. And if you've had a chance to take a look at your homework, you'll see quite a bit of it is on these 6 W's. The 6 W's are who, what, when, where, why, and how. So as far as data description goes, who is to describe the individuals who are being studied or surveyed. What is to determine what is being measured. When has the research conducted, or when was the research conducted, excuse me. Where was the research conducted. Why. Why. In other words, what was the purpose of the survey or the experiment? Why was the survey or experiment conducted? And how, to describe how the survey or experiment was conducted. Not all of these are given to you in every scenario, but The ones that are, you should be able to identify, and you should also know which ones haven't been given to you. So as far as who or what goes, in general, the rows of a data table correspond to individual cases about whom or which we record some characteristics. Rows are sometimes referred to as records. Cases go by different names depending on the situation. So, what do I mean by that? Individuals who answer a survey are often called respondents. People who we perform an experiment on are often called subjects or participants. But when we do an experiment on non-people, such as animals, plants, websites, or any other inanimate object or subject, we call those experimental units. Depending on your major and what kind of data you're going to be working on in your future careers, you should be familiar with how the who's are classified. Let's take a look at an example. Ian Walker, a university psychologist, wondered whether drivers treat bicycle riders differently when they wear helmets. He rigged his bicycle with an ultrasonic sensor that could measure how close each car was that passed him. He then rode on alternating days with and without a helmet. Out of 2,500 cars passing him, he found that when he wore his helmet, motorists passed 3.35 inches closer to him on average than when his head was bare. For this scenario, we wanted to describe the who and the what. Just a review, who describes the individuals who are studied, and what determines what is being measured. In this case, the who is the 2,500 cars. Wow, I see I've had a couple typos here. So who is the 2,500 cars? What is the distance from car to bicycle? So again, what is being measured, or the people being studied, excuse me, who's being studied, what is being measured. Our population is all cars passing bicyclists. Let's take a look at another example. Because of the difficulty of weighing a bear in the woods, researchers caught and measured 54 bears, recording their weight, neck size, length, and sex. They hoped to find a way to estimate weight from other, more easily determined quantities. Let's identify the who, what, when, where, why, and how. Who? Who is the 54 bears being measured? So each bear is considered to be an individual case. What is what we've measured? We've measured their weight, neck size, length, and sex. We were not given when this was occurring or where this was occurring. Why is this occurring? Well, we're trying to estimate weight from easier to measure variables, and how. Researchers have collected data on 54 bears that they were able to catch. Let's take a second to make sure we know how to classify between quantitative and categorical, almost said qualitative, variables. So from our bear example, weight. Is weight going to be quantitative or categorical? Well, in my experience, weight is quantitative, numeric. Neck size, same thing, quantitative. Length, another number, quantitative. Sex, that is categorical, male, female. All right, so as we are wrapping up this first lecture, there is one more thing I want to talk about, and that is models. So basically, what do we do with these data that we're collecting? How can we take 54 bears and their information and make that meaningful, usable. And we do that with models. Models are summaries and simplification of data that help our understanding and can help provide explanation to others. A model is a simplification of reality that gives us information that we can learn from and use. There is a very famous saying in statistics that all models are wrong, but some are useful. So it's pretty much impossible to make a model that is 100% perfect. There's too many variables to account for every possible situation. But models generally give us, again, it's a simplification of reality. So they give us a good estimate of what we're expecting to occur. So while measuring, say, the neck size, length, and sex of a bear may not give us the exact weight, but it can give us a good approximation. If you're still not quite sure what models are, you actually are probably familiar with them. If you think back to your 8th grade math classes, you probably learned how to create a line of best fit for a scatter plot, where you had a scatter plot and you needed to draw a line through as many points as possible to kind of demonstrate the trend. This is a model. This line isn't going to hit every single data point, but it will show us the general trend, and it provides a good estimate when we aren't able to measure something exactly. That's a model. It's our simplification of reality to give us an idea of what we can predict and use in the future. As you saw, we had a scatter plot, which does tell us that we are sometimes going to need to visualize data. And honestly, making a picture is one of the best ways to examine, understand, and explain your data. Our next lecture is going to focus more on different methods of visualizing data, which, as you can imagine, is very, very important for us as statisticians. So that does bring us to the end of this first lecture. As I will end every lecture, if you have any questions, please send me an email. Have a great day.